This is your tutor Pragya Sahu. This PMRF scholar at the Department of Chemistry, IT Kanpur. So today we will read the first law of thermodynamics. Then we will read the mathematical form. After that, we will solve some problems related to that. Okay. So before that, let us first study what is zeroth law of thermodynamics. So zeroth law of thermodynamics states that if two systems are separately in thermal equilibrium with a third one, then they tend to be in thermal equilibrium with themselves. Let's say we have two systems, B and C. Okay, we have two systems B and C. Okay, and this B is in equilibrium with system A. Okay, this B is in equilibrium with this system A. Also, this system C is in equilibrium with system A. So this system C is also is in equilibrium with system A. Okay. Now what zeroth law of thermodynamics states that if B is in equilibrium with A and C is in equilibrium with A, then these systems B and C will also be in thermal equilibrium. Okay. Then they will also be in thermal equilibrium. Okay. So yeah. So in this picture, they have shown that the system A is in equilibrium with B, and the system A is in also equilibrium with C. Then this is zeroth law of thermodynamics states that this system B and C will also be in thermal equilibrium with each other. This is also the principle by which the thermometers are used. Okay. Okay. So now we have to study the first law of thermodynamics. But before that, the first law of thermodynamics uses the term heat, internal energy, and work. So we should be very clear with this term. So let us first just quickly recall what are these. I have already discussed this in earlier class. So internal energy. What was internal energy? That every system having some quantity of matter is associated with a definite amount of energy. So it is the energy contained within the system. Okay? So let us say this is the system and it contains 1 mole of gas. So if this system contains 1 mole of gas, then and energy will also be associated with the system. Okay, and that energy associated or contained in the system will be called as the internal energy of the system. Energy contained within the system will be called as internal energy of the system. Internal energy of the system. And internal energy is denoted by U. It is denoted by symbol U. Okay, U, capital U. Okay, so it can be any energy, any form of energy. You can think of mechanical energy or electrical energy, chemical energy, any kind of energy. Then and if we take the sum of all these form of energies, it will be then for a system it will be called as the internal energy of a. So here it is written that the sum of all energies, i.e. the total, if we sum all the energies, then what will be called? The total energy. Okay. So the total energy of the system is called as the internal energy of the system. This is what we have studied about the internal energy. And next we have work. So work is the transfer of energy between a system and its surrounding through the application of force over a distance. Okay. So work is nothing but the transfer of energy between system and the surrounding. Okay. Next we have heat. So heat is the transfer of energy between a system and surrounding, but here due to the temperature difference. Okay. This is very important. Here it is due to the temperature difference. Okay. Let us go back to the first law of thermodynamics. So the first law of thermodynamics, it is also known as the law of conservation of energy. So this is also known as the law of conservation of energy, and it states that the total energy of an isolated system. Okay, so this is for an isolated system. So the total energy of an isolated system remains constant. Okay, so it remains constant. That means it doesn't change, though it may change from one form to another. Okay, it remains constant, but it can change from one form to another. Okay, so the first law of thermodynamics states that the the total energy of the total energy of an isolated system remains constant. Okay, this basically means that there is a statement which states that the energy of an isolated system, this is the same statement, the energy of an isolated system. So this first law of thermodynamics can be you can there are many forms of first law of thermodynamics. Okay, we can uh, also say here it is written that it, it is other, yeah, these are the other statements of first law of thermodynamics. Okay, so these are the statements which I am writing over here. These are the statements of other statements of the first law of thermodynamics, of which one is the energy of an isolated system remains constant, is constant. Okay, this is one of the statement of the first law of thermodynamics. Okay, however, it can be changed from one form to another form. Okay, now it is written that when a system moves from state 1 to state 2, let us consider two states, states 1 and state 2. So this is your state 1. Okay, I'll just add a slide to explain this to you. Okay, let us explain it over here only. One second. Yeah. So this is your state 1. So and it is fitted with a piston. This is a piston. This is state 1. Let's say it contains 1 mole of an ideal gas. Okay? 1 mole of an ideal. So this is the state 1. Now let us consider this state 2. If we this is your piston. If we provide heat to the system, okay, let's say we are supplying heat to the system. We are supplying heat to the system. And how heat is denoted? It is denoted by Q, capital Q, capital Q or small q. Okay. So Q is the amount of heat that is being supplied to the system. Okay. So here in this is small. If this is the case, then what will happen? If heat is getting applied to the system, then what will happen? The piston will start moving upward. Okay. So now what will happen? It will go under different thermodynamic system or different state where your piston will come over here. It will move upward and your gas will occupy this much. Okay. This is again the same 1 mole of gas, but the piston has moved this much. Okay, because what we are doing, we are applying heat to the system. So this is what a thermodynamic process. A thermodynamic process. And yes, this is state one is this is state two is totally different from the state one. Okay, this is the state two. It is totally different from the state one. Okay. If if the internal energy of the system was U, let's say initially the internal energy of the system was U. So internal energy of system was U. Okay, and if W, now this is the work done. Okay, work done in moving the piston. So work is done here by the system. Okay, here work done by the system. Okay, so if this is the case, so what if this is the case where your system state one is going under a thermodynamic change and it forms a state two, then the first law of thermodynamics states that in a thermodynamic process involving a closed system, the increment in the internal energy, that we are basically increasing the internal energy. So the increase by applying this heat. So the increment in the internal energy equal to the difference between the heat accumulated by the system and the work done by heat. Okay. So okay, I'll add a page over here because I'll have to write a few things and then explain it to you also. Okay. So I'll write over here that the first law of thermodynamics states that a thermodynamic process involving so if a thermodynamic process involves the increment of closed system, okay, okay, if a thermodynamic change is getting involved in a closed system, then the increment in the internal energy, that is the increase in the internal energy, the increment in the internal energy is equal to the what is equal to the difference between the heat accumulated, difference between the heat accumulated by the system and the work done by it. Basically, it states that the increment in the internal energy, what will be the increment in the internal energy? Delta U. Increment in internal energy is nothing but the change in the internal energy. Okay, so change in internal energy is what? Final internal energy minus initial internal energy. Okay, let's say final internal energy was U2 and initial internal energy was U1. And we know that change in internal energy is denoted by delta U. So your delta U, that is change in internal energy, is nothing but U2 minus U1. Okay, that is final minus initial. Then it states that increment in internal energy, that is the change or increase in the internal energy, is equal to the difference between the heat accumulated by the system. So heat accumulated by the system is what? What amount of heat we had applied in that case? Q. Okay. Divided by the W. Okay. So it will be Q minus, just a second, that my, oh, sorry. So it is one second. So it is Q minus of Q minus W. Okay. So where Q represents the heat supplied to the system, and W represents the work done by the system, and delta U represents the change in internal energy. Okay. So just a second, something just happened over here. Okay. It might be working now. Yeah, it is working. Okay. So the change in internal energy is equal to the heat supplied to the system minus the work done by the system. So this is your the mathematical equation for the first law of thermodynamics. First law of thermodynamics, where Q represents the heat supplied to the system, and your W represents work done by the system. Okay, so this is your this statement of the mathematical equation for the first law of thermodynamics. Okay, let us go back to where we were. So here it is written that when a system moves from state 1 to state 2, this is state 1 to state 2, its internal energy changes from U1 to, if U1 was internal energy initially, and U2 was its final internal energy. Then its internal energy changes from U1 to U2, and the change in internal energy, that is delta U, is denoted by U2 minus U1. And then this internal energy change is brought about by either absorption or diffusion of heat. Here in this case, we are supplying heat to the system. So that means here we are studying the case of absorption of heat. Okay. What if heat is getting evolved from the system? Then in that case, we will do work on the system. Okay. So in that case, the work will be done on the system. Okay. So here it is in that because the total energy of the system must remain constant, which is nothing but the statement of the first law of thermodynamics. We can write that the delta U, that is the change in internal energy, is Q plus W. Okay. So here plus sign is there. Why? Because here heat is applied to the system and also work is done on the system. Okay. If work is done on the system, then we will use plus sign. Okay, this is why they have used plus sign over here. You know that. Okay, let me again clear it. If work is done on the system, then we use positive sign. Then we use plus positive sign. Okay, that means plus of W. And if work is done by the system, like if your system is doing work, then we are going to use minus of W. Okay. So this is the reason why they have used plus of W over here, because here work is done on the system, and what we studied over here, we studied a process where work is done by the system. That's why we are getting the delta U as Q minus of W, because in that case work was done that in this case. Okay. Let us move to the next slide now. Okay. So this we have already studied, and now we have also studied the sign convention for work. Okay, so that is very important. You must remember, and that heat is denoted by U. And same with the heat. If heat is supplied to the system, then it is taken as plus of Q. If heat is taken out of the system, then it is as minus Q. Okay, so if heat is supplied to the system, then we use plus of Q, and if heat is taken out of the system, then we use minus Q. Okay, we will solve a problem related to that, and then we will our doubt will be cleared with those problems. Okay, so it is very simple. With practice, you will get that. Okay, so these are the other statements of the first law of thermodynamics. So here in first case, they have written that whenever an energy of a particular type disappears. Okay, so let's say we have some form of energy. Let's say we have heat energy. Okay. So if we are dissipating this heat energy, like we are giving this heat energy to some, let's say some machine, and this machine is converting, this machine is doing work. Okay, so your heat energy is getting converted to some different form of energy. Okay, so when an energy of a particular type disappears, that means your heat energy getting heat is getting consumed. That means your heat is getting disappeared. An equivalent amount of another type must be produced. See, if you are giving it to the machine, then and work in the form of, let's say, mechanical energy. Okay, then your heat is getting converted into the mechanical energy. That means it is getting converted into one form from one form to another form. Okay, but okay, so yeah, this was the first statement. And next is the total energy of a system and surrounding remains constant, or which is also said it is constant. Okay, so let's say this is your system. Okay, and this is your surrounding. Let's say initially its energy was here, and somehow this system does some work to the surrounding. Okay, and what will happen? The energy of the system will decrease, and the energy of the surrounding will increase, but overall it will remain constant. Okay, so if it is getting used by the system and being supplied to the surrounding, then that means somehow it is remaining constant. Okay, so if something happens and system energy decreases and it gets supplied to the surrounding, okay, then the total energy which was initially E, it will, for this case, it will also be E. Okay, this was your system. Then again, it will remain as E for the whole system. Okay, for the whole case. So the total energy of the system and your surrounding, the total energy of the system and your surrounding, this was the surrounding, will remain constant or conserved. Like initially if it was E, then finally, okay, there may be change between the energy of system and surrounding, but the whole as a whole they it will remain constant. So what is system and surrounding called? If we add whole system and surrounding, what is called it? What we call it? Universe. Okay. So the another statement of the first law of thermodynamics is also that the energy of the universe is constant. Okay. This is very important statement, that the energy of the total energy of the system, that means here it system and its surrounding. So for if we add system and surrounding, then what will be we call it universe. Then that means the energy of the universe will remain constant. And we can also, if it remains constant, then what we can say, that it can neither be created nor destroyed. So these are different forms of statement. Like if this remains constant, this basically means that it can neither be created and not be destroyed. However, it as told earlier, that it can be converted from one form to that. Here in this case, it was converted to heat energy to mechanical energy. So now, but maybe it may be converted from one form to another form. So this is very important statement, that which says that energy can neither be created, we cannot create energy, neither we can destroy it, but we can convert it from one form to another form. Okay. Next one, we have the change in internal energy of a closed system is equal to the energy that passes through its boundary as heat or work. Okay, so this is nothing but this statement which says that the change in the internal energy of a closed system, that is delta U, is equal to the energy that passes through its boundary as heat or work. Okay, because your internal energy can be changed either by heat, by supplying heat, or it can be changed either by doing work. Okay, so this is what they have said, that the change in internal energy is nothing but it is equal to the energy that passes through its boundary as heat or work. Next, we have the heat and work are, yeah, which basically says that the We can change the a system's internal energy by doing heat, by supplying heat or taking out heat, or by doing work on the system, or by work if your system does the work. Like that means work is done by the system. So these are the two ways, that is heat and work. They are the ways of changing the system's internal energy. Yeah. Okay. So this is the mathematical statement of the first law. I have already told you that your delta U was Q minus W. Your system does the work, and it is Q plus the W, and it is Q plus W if you are doing work on the system. Okay. So the mathematical statement of first law of thermodynamics plus W, here they have used plus, that means work is done on the system. Okay. So now we have some cases where we have to calculate the change in internal energy. So for that processes, we have to calculate what is the change in internal energy. Like we have many processes, like cyclic processes and isobaric processes. Okay. So in that cases, if we are doing, then according to any change, then according to first law of thermodynamics, what will be the change in the internal energy? Okay. So let us first solve this case first. So for a cyclic process involving isothermal expansion of an ideal gas, so we have to calculate delta U, that is change in internal energy for a cyclic process. We know that for a cyclic process, and if it involves isothermal expansion of an ideal gas, then your internal energy is zero. Okay, because see, if cyclic process means, if it was firstly it was in state A, and we do some work, and we again reach the state A, then do you think there will be change in the internal energy of the system A? No, because its initial and final state is same. Initial state and final state is same. Then there will be no change in internal energy. No change in internal energy. Okay. So your delta U is zero. If your delta U is zero, okay, then what will happen? Delta U is nothing but Q plus W. This means Q plus W is equal to zero. If this is the case, then Q will be equal to minus of W. So it is over here that Q is equal to minus of W. So if this is the case, then during a cyclic process, it means that what this mathematical is, that during a cyclic process, the amount of heat absorbed, that is Q, by the system is equal to the work done by the system. Here minus sign is shown, that means work is done by the system. Then that means that the amount of heat we are supplying to the system, that heat is getting absorbed by the system. Then it is uh, used to do work. Okay. Then what does it mean? Your system is doing work. That means your work is done by the system. Okay. So the amount of heat absorbed by the system is equal to the work done by the system. So the second case is for an isochoric process. For an isochoric process means your volume is constant, and if volume is constant, then let's say your initial volume is given and final volume is given. Then change in volume is V2 minus V1. Okay. If volume is remaining constant, that means V1 is equal to V2. And if that is the case, if V1 equal to V2 here, then your delta V, that is change in volume, equal to 0. Okay. That means your volume is not getting changed. That means your volume remains constant. That means the change in volume will be 0. So if delta V is 0, we know that delta U equal to Q plus W. Okay. And W is what? Minus P delta V. You know that W equal to minus of P into delta V. So let us substitute over here minus delta V. We know that delta V is 0. So multiplying 0 with P will also give 0. Okay. So this whole term will become 0. So what will remain? Delta U is equal to Q. So as we are taking this is an isochloric process, we can write it to P because volume is constant. Okay. So this is nothing but the change in the amount of heat supplied to the system at constant volume is nothing but it will be equal to the change in internal energy of this. So the amount of heat supplied to the system, this is very important statement. Heat supplied to the system at constant volume equal to volume equal to the change in internal energy. Okay? So the amount of heat supplied to the system, that is Q at constant volume, that is QV, will be equal to the change in internal energy, that is delta U. Okay? And for an adiabatic process, okay, so this is the third case. For an adiabatic process, we know that Q is equal to 0. Okay? There is no change in heat. If there is no change in heat, then that means Q equal to 0. We know that delta U equal to Q plus W from first law of thermodynamics. So if your Q is equal to 0, that means your delta U will be equal to W only. What does it mean? It means that for an adiabatic process, the decrease in the internal energy is exactly equal to the work done by the system. Okay? The decrease in the internal energy will be exactly equal to the work done by the system on its surroundings. Okay? Next, we have an isobaric process. For an isobaric process, the pressure remains constant. Okay. For an isobaric process, your pressure remains constant. That means there is no change in the pressure. So if your delta U is Q plus W, okay, this is the first of mathematical statement of the first law. Then delta U will be equal to Q and minus of PdV, as work done is equal to nothing but minus of PdV. So this is the internal energy of the system for an isobaric process. So in other words, in an isobaric process, a part of heat absorbed by the system, that means the heat absorbed by the system, is used for PV expansion work. Okay, it is used for the PV expansion work, and the remaining is added to the internal energy of the system. Okay, if Q was the heat absorbed by the system, then it does some work. Okay, so if it does some work, then what is work? Minus PdV. So this amount it will be get used by the system. So and what will be the internal energy? That Q minus of the PdV. Okay. So increase in the internal energy will be the difference of this Q and PdV. Okay. So this is what the fourth. Okay. Let us solve some problems now. So here the problem 1 is a gas contained in a cylinder fitted with a frictionless piston Okay. Expands against a constant external pressure of 180. So P external given as 180. So a gas contained in a cylinder fitted with a piston stands against a constant external pressure of 180 from a volume 5 liter to volume of 10 liter. So initial volume is given as 5 liter and final volume, that is V2, given as 10 liter. Okay. So in doing so, it absorbs 400 joule of thermal energy. So what is the energy? Which is heat. Okay, so 400 joule of thermal energy from its surroundings. So basically, we are providing heat for doing work by the system, in which the volume changes from 5 to 10 liters. Okay. Determine the change in internal energy of the system. Now we have asked calculate change in for the cylinder. Fitted with the piston. Okay. Of hydrogen. So initially the volume was 5 liters, and we applied few amount of heat to the system. Then what will happen? Which is 400 joule. The piston will move upward and its volumes will change. So if volume gets changed, sorry, so if its volume gets changed, now it is the piston moves upward. Let's say over here. Now the volume is 10 liter. Okay. So now they have asked the internal energy, change in internal energy. Okay. So we have asked to calculate the change in internal energy. So we know that delta U is equal to Q plus of W. We use plus W if work is done on the system. But here you can see that here work is done by the system. So in this case, if work is done by the system, then we will use Q minus W. Okay. We will use Q minus of W. Okay. So Q is given 400 joules minus W is what? P into dV. Okay. So if this is the case, then 400 joules minus pressure is 1 atm and dV is nothing but V2 minus V1, change in volume. So V2 is 10 liters minus V1 is 5 liters. It will give us 5 liters. So dV is 5 liters. So 1 atm into 5 liters. Now let us solve it over here. In order to change liter atm into joule, we have to multiply it with 101.33. So 1 liter atm is equal to 101.33 joule. Okay. So if 1 liter atm is equal to 101.33 joule, then here we have 5 liter atm. Then we will multiply 5 with 101.33 and we get liter atm in joule. Okay. So what will we get? Data use equal to 400 minus 5. If we are changing 1 liter atm to 101.33, we will get it in joule. Okay. So if you solve this, you will get 400 joule minus 506.65 joule, which will give you delta U is equal to minus 106.65. Okay. So if you solve this, you will get change in internal energy in joules, which is minus of 101.65 joules. And if it is minus, then what does it mean? That your internal energy of the system is decreasing. Okay? That the internal energy of the system is decreasing. Okay? So we have solved this question. Okay? Uh, what we have determined the changes in the internal energy of the system and we have calculated change in the internal energy. Okay, we have solved this problem. So see, we just have to what we have just used. We have just used is the mathematical statement of the first law of thermodynamics. First law. Okay, and what we have to keep in mind that we the sign of the work done. Okay, so if work is done by the system, in that case you have to use negative sign over here, and if work is done by on the system, then you will use the positive sign. Okay, okay. Let us move to the next problem now. It is express the change in internal energy of the system. When so we express the change in the internal energy, that is delta U, and then we have given this condition. Let us do this. So first case is when no heat is absorbed by the system. Heat is what? Q. That means your system is not absorbing heat. If your system is not absorbing heat, then that is Q is equal to 0. Okay. No heat is absorbed by the system from the surrounding. Okay. So if this is your system, okay, and it is not absorbing any heat from the surrounding, then what comes? Then it Q will be equal to 0. But work is done on the system. But you are doing work on the system. Okay. So if you are doing work on the system, so if here work is done on the system. So what I have told you, if work is done on the system, then we use plus of W positive sign. Okay. So what will be your work? Plus of W. Now we have to calculate the change in internal energy. So change in internal energy is nothing but Q plus W. Okay, from the first law of thermodynamics. So here work is done on the system. So we will have to use the positive sign. So positive sign is already over here. So we will not change it. But Q is 0. So let us put Q equal to 0 in this equation. What will we get? 0 plus of W. What will it give? Delta U equal to W. So we have calculated the change in internal energy, but now they have asked that what type of force does this system have? We know that if a system does not absorb heat, okay, so if if your system is not absorbing heat, then what kind of wall it will have? Adiabatic wall, okay. Because in case of adiabatic processes, your uh, heat remains constant. Okay, your Q doesn't change. Your system doesn't absorb heat. Okay, so in that case, that the process is called as adiabatic process, and the walls are called as adiabatic walls. So we have left the answer. Delta U is nothing but the adiabatic work done, and what type of fault does the system have? We have adiabatic. Okay, so this is the answer of first. Next, what if no work is done on the system? Okay, so now work done on the system, that is plus W equal to 0. So if work done on the system is 0, but Q is the amount of heat taken out from the system. So here, if heat is taken out from the system, then I have told you that we will use minus of Q, because heat is taking out of your system. So if heat is taken out of the system, then we use minus of Q. Okay? Then if we use minus of Q, and it is given to its surrounding. Okay, so what? So now we have to calculate delta U. So delta U is Q plus W. Okay, this is from first law, but here heat is taken out from the system, so Q will become negative. So delta U, if we use negative sign, it will become minus of Q plus work done. Work done in this case is 0. So it will give us delta U equal to minus of. And now they have asked what type of wall does the system have. So in this case, if your system can exchange heat, your system can exchange heat, then in this case, this kind of walls are called as thermally conducting walls. Okay, so these are called as thermally conducting. So we have also solved this question that your delta change in internal energy is equal to minus of Q, and walls will be called as thermally conducting. Let's solve the next question. Okay. So here they have asked to express the internal energy when W is the amount of work is done by the system. So okay, if work is done by the system, then we will use minus of negative, minus of W. Okay, and Q is the amount of heat supplied to the system. So if heat is supplied to the system, then what will become? Plus of Q, because it is not in case of if heat was taken out from the system, then it was minus of Q. And here if it is added to the system, then it will be plus of Q. Then what will be your change in internal energy? That is delta U, Q plus W. So if we use this, what will it become? Delta U is equal to Q will be plus of Q, and your work will be minus of W. So it will give you delta U equal to Q minus W. Okay. And next they have asked what type of system would it be? Okay. If you, okay, so if you are applying heat to a system, okay, you are applying heat to a system. Let's say initially it was air, this was gas. So what will happen? The piston will move upward. Okay. Now it is like this. Okay. So what kind of system it is? It is a closed system. Why? Because you are supplying heat to the system, and your system, that is your gases, uh, applied force on this piston, and this piston moves upward. So this work is done by the gear work is done by the system. So this kind of Some are called as processes. So we have process. So these are the problems we have solved today. And this kind of questions you will be get asked in NEET and JEE. Okay. So this kind of question they ask. So what we studied today is the zeroth law of thermodynamics. Okay. Then in order to understand the first law of thermodynamics, we studied basics, that what are the internal energy, work and heat. Then we studied the uh, statement of the first law of thermodynamics, which is also known as the law of conservation of energy. That is, energy remains constant. Okay, that means energy of the universe remains constant. Okay, then we derive the mathematical statement of the first law. Okay, here, then we derive the mathematical statement of the first law, that is delta U is equal to plus W, and then we calculated the change in internal energy for various processes, like for cyclic processes, for isophoric and adiabatic, and then isobaric process. Okay. Uh, then we came to the question and solved and understand what basically they are asked. Okay. So this is what we have studied in this lecture. In this lecture, uh, we will continue further. Okay. So I'm ending this session now.